Hey guys, as you've probably realized by now, there are a lot of concepts which involve differential calculus. So for example, the fact that the instantaneous rate of change of a function can be found through the slope of a tangent line to that function at a specific point, or the fact that a function is increasing whenever the slope of a tangent is positive at that given point or interval, or that points of inflection are found whenever the concavity changes from positive to negative or negative to positive. So there are many things that you need to know how to find, how to apply, and how to use in different IB math exercises. Now, there's one specific type of exercise which is not exactly in sync with the IB math curriculum. However, it requires you to know all these things at the same time. It is not common to see an exercise with curve sketching, which means sketching a curve using the first, the second derivatives, using limits. However, if you're able to run through this process, to go through this process flawlessly, that means that you understood all the concepts in differential calculus, and that in itself is a very valuable skill to develop. Therefore, we're going to go through this process, which is, like I said, not exactly in sync with IB math style exercises. This is more college calculus. However, this is an excellent way to practice all the concepts in differential calculus. So the exercise is the following. We're going to sketch this function f of x, which is e to the x minus x plus 1 over x minus 1, using not only information about the function itself, such as domain, symmetry, and behavior, but also using derivatives, meaning the first and the second derivatives. We're going to go through, for example, the first derivative test, the second derivative test. We're going to talk about points of inflection, maxes and mins, everything. The algorithm or the step-by-step process is laid out over here. We're going to start with the domain, then intercept, symmetry, asymptotes, find increasing and decreasing intervals, then concavity, coordinates of key points, which are the points that we found in the previous items, such as x-intercepts, y-intercepts, points of inflection, maxes and mins. And lastly, we're going to sketch this curve. So starting with the domain. This function is not purely rational. However, we do have a denominator to worry about. We cannot divide by 0. Therefore, we need to guarantee that x minus 1 is not equal to 0, meaning x cannot be equal to 1. Therefore, the domain of this function is all real numbers except for 1. Do notice as well that there's no restriction with the numerator. Step number 2, we're going to find the intercepts, more precisely the y-intercept, given that this function does not have any x-intercepts. In order to find the y-intercept, we're going to replace x by 0, meaning we're going to have e to the 0, which is 1, minus 0 plus 1 over 0 minus 1. So this is equal to 2 over negative 1, which is equal to negative 2. Therefore, 0 comma negative 2 is one of the points that the graph of this function crosses. If you wanted to find x-intercepts, you would need to take the function, which is e to the x minus x plus 1 over x minus 1, and set it equal to 0, meaning if you cross multiply, you'll be finding points where e to the x minus x plus 1 is equal to 0. Now, it's a little bit beyond the scope of this video, but do know that there's no solution for this equation. Therefore, there's no x-intercept. Now, number 3, and we're yet not talking about derivatives, not yet. Symmetry can be found when we replace x by negative x. And if we find that f of negative x is equal to f of x, that means that the function is even, which means that it's symmetric about the y-axis. The y-axis serves as a mirror. If by replacing x by negative x, you get the same expression as negative f of x, meaning the negative version of the function, that means that the function is odd, which means that it's symmetric about the origin. Now, these are not the only two cases. The last case, which is actually the most common one, is not to have any type of symmetry. Therefore, f of negative x not being equal to f of x and not being equal to negative f of x, which is exactly what's going to happen right here. When replacing x by negative x, we get e to the negative x minus negative x plus 1, meaning x plus 1, all that over negative x minus 1. And this is not equal to f of x, and it's also not equal to negative f of x. Therefore, this function is neither even nor odd. Now on to step number 4, asymptotes. We can see that we have a vertical asymptote, which means a discontinuity in this example at x equals 1. So we have a vertical asymptote, which is x equals 1. Now, in order to test whether we have a horizontal asymptote, we need to calculate the limits of this function as x approaches positive infinity and negative infinity. We're going to start with positive infinity. So we're going to find the limit as x approaches infinity of e to the x minus x plus 1 over x minus 1. Notice that the influence of this plus 1 and of this negative 1 as x grows a lot can be neglected. Therefore, we can rewrite this limit as e to the x minus x over x, which we can break down into two. The first one being the limit as x approaches infinity of e to the x over x, which gives us an indeterminate form, infinity over infinity, so we need to use L'Hopital's rule over here, plus negative, so you can write a negative sign over here, the limit as x approaches infinity of x over x, which is just 1. Therefore, limit of 1, this is just 1 as well. So applying L'Hopital in the first limit, we have the limit of the derivative of e to the x over the derivative of x, which is 1, minus that 1 that we found previously. Now this limit right here, e to the x over 1, as x grows, it will grow to infinity. Therefore, we have over here positive infinity, which means that we don't have, by looking at the limits as x approaches positive infinity, a horizontal asymptote. Now let's do the same as x approaches negative infinity. We have e to the x minus x plus 1, again, over x minus 1. And again, the influence of positive 1 and negative 1 can be neglected. Therefore, we have the limit as x approaches negative infinity of e to the x minus x over x. And again, we can break it down into two limits. But now in this case, this negative 1 over here will prevail, given that as x approaches negative infinity, the numerator will approach 0, given that we have e to the negative infinity. So e to the negative exponent, and that exponent being really big, it's just going to lead to a number which is very close to 0. And after we divide that by a gigantic negative number, well, that's just going to make this approach 0 even faster. So the answer over here is negative 1. And the negative 1, of course, comes from here. All right, so we're halfway through. We need to tackle the increasing and decreasing intervals, concavity, coordinates of key points, and sketching the curve. So let's jump to step number 5. And actually, before going to step number 5, we can already place some information that we already have into the graph of this function. So let's do that right now. We can already draw the coordinate plane and place the horizontal asymptote over here, and also the vertical one, which is x equals 1. We had a few steps before found the y-intercept, which is 0, negative 2, which is this point right here. So let's place it over here. And perfect. Now we can go to step number 5. To find increasing and decreasing intervals, we first need to calculate the first derivative. And given that this is the function that we have, using the quotient rule, we have the following. The first derivative is the derivative of the numerator, which is e to the x minus 1, times the denominator, minus the numerator times the derivative of the denominator over the denominator squared, which we can simplify a bit. So we have x e to the x minus e to the x minus x plus 1 minus e to the x plus x minus 1. So we can simplify these and leave the x minus 1 squared in the denominator. And given that we have negative 2 e to the x, we can factor e to the x out and get x minus 2 over here. everything over x minus 1 squared. Now, one thing that you need to ask yourself is, where's the critical point? Where's the critical value? And that is when the first derivative is equal to 0. So we're going to take this function, f prime, and make it equal to 0 and set it equal to 0. And by cross multiplying x minus 1 squared, we get e to the x minus 2 equals 0, which we can break down into two possibilities. Either e to the x is equal to 0, which has no solution, or x minus 2 equals 0, therefore x equals 2. So this is a critical point or stationary point. And how we're going to verify that? How we're going to verify whether this is a min or a max? We can use the first derivative test, which means that we're going to draw a number line, place the critical point over here. We are also going to place the point at which the function is discontinuous, which in this case is 1. And by substituting values within these intervals, we will find the sign of the first derivative for those intervals. So we can use, for example, 0, 3 over 2, and 5, and find f prime of 0, f prime of 3 over 2, and f prime of 5. F prime of 0 is, for example, e to the 0, 0 minus 2, over negative 1 squared. So we get negative 2 as an answer. We don't care whether it's negative 2 or negative 10. We only care about its sign, and the sign is negative. That's the only thing that matters. In this interval, given that this sign is negative, the function, it is decreasing. And if you do the same thing with 3 over 2 and 5, you find a negative value and a positive one, which means that over here the function is decreasing and over here the function is increasing. So color coding, this is what we have. I'll place these intervals in our graph as well. So negative infinity to 1 and also 1 to 2. These are our decreasing intervals and increasing from 2 to positive infinity. Given that at 2, the function goes from decreasing to increasing, we have a local minimum. And it's important to find the coordinates of this minimum. So it's 2, comma, f of 2. And we can find f of 2 by replacing 2 into our function. It is equal to e squared minus 2 plus 1 over 2 minus 1. Therefore, e squared minus 1. So 2 comma e squared minus 1. We can plot this point as well. 2 comma e squared minus 1. So 2 comma something like 6.4-ish. So this will be a local min. And by the way, we're already tackling this 7th step right here, which is to find the coordinates of some key points. And now let's jump to step number 6, which is concavity and point of inflection. For that, we need to differentiate the function again. We're going to start with the first derivative. And by differentiating it again, we have the following. F prime prime of x equals, careful because we have a product rule over here. So we have the derivative of the numerator, which is a product, e to the x times x minus 2 plus e to the x times the derivative of x minus 2. And this is only the derivative of the numerator times the denominator, x minus 1 squared, minus e to the x minus 2, which is the numerator, times the derivative of the denominator, which has a chain rule in it, or it requires a chain rule, which is 2x minus 1 to the first power times 1, so 2 times x minus 1, everything over x minus 1 squared, meaning to the fourth power. We can simplify one term, x minus 1, from each one of these, giving us 1 and 3 over here. And after simplifying this expression even further, you should get x squared e to the x minus 4x e to the x plus 5 e to the x, and we can put e to the x as a common factor in the numerator, everything over x minus 1 cubed. Now, by doing just that, and before defining where the function is concave up or down or where's the inflection point, we need to take this second derivative and make it equal to 0 and set it equal to 0. Which means that we need to solve the following equation. E to the x, x squared minus 4x plus 5 equals 0. We can break this down into two again. So either e to the x is equal to 0, which has no solution, or x squared minus 4x plus 5 equals 0, which has no solution as well. Now you might be wondering what you should even place in the number line, given that you never found a solution for none of these, in order to establish where the function is concave up or down. There's one thing that we need to place in the number line, and that's always the case when we have a discontinuity, which is the point where the function is discontinuous. So we're going to use the number line with 1 showing where the function is discontinuous. And we're going to use numbers which are to the left and to the right of 1 to establish whether it is concave up or down in these intervals. Now we can replace, for example, 0 and 2 into the second derivative of f. So calculating f prime prime of 0 and of 2, we get a negative number and a positive 1 respectively, meaning and concave up from 1 to positive infinity. And let's color code these intervals as well and place these intervals into our graph as well. So from negative infinity all the way to 1, the curve is concave down. And from 1 to positive infinity, the curve is concave up. Now, one thing that you might be wondering is whether x equals 1 represents an inflection point. And the answer is no, because the function is not defined when x is equal to 1. All right, so we have all the data that we need in order to finish this curve. We have a minimum point over here, which means that the function, the curve, will be something like this. We'll have this behavior. We also know that x equals 1 is a vertical asymptote, which means that the curve will go up over here. And in order for it to cross this point, it needs to come from negative infinity if you're considering x equals 1, and it will approach the line y equals negative 1 as it goes to the left. So let me just remove a little bit from the left over here, and we can complete the sketch of this curve. And also very important, notice that this is being drawn in a way for the curve to be concave down from negative infinity to positive 1 and concave up from 1 to positive infinity. And also notice, and let me remove a bit of the excess from the right over here as well. Also notice that the function is really decreasing from negative infinity to 1 and from 1 to 2, which can be verified by drawing tangent lines. You can notice that all of these tangents, they have negative slopes, and the curve is increasing from positive 2 to positive infinity, which can be verified as well through slopes of tangents. And there we go. This is the graph of f of x. You can always compare, of course, using GeoGebra or your GDC to the actual curve, the curve that a software provides you. Now, this is it, sketching a curve using derivatives.